Okay, let's talk briefly about this problem from, as you can see, I've taken a bad image, a photo of my screen in Microsoft Word, from the Canadian Mathematics Olympiad in 1991, and it asks us to consider the geometric locus of the midpoints of the set of chords that pass through a point P inside a circle. And you can see I've already started the diagram for us, so we can start to understand this. And so straight away, what I want to talk about is kind of how people in general might go about solving geometric problems. And really, I'm only talking from my own experience, but this is kind of the way that I see it. And when you're actually solving a problem, it's pretty easy to forget how to solve them, how to think about solving them, which is why I'm making this video in the first place. So to start with, we have this big advantage that we're told that the geometric locus is in fact a circle. So let's use that and let's look for the center of that circle. I would say use the advantages that you're given in the question. So we have our point P drawn, and we have all these chords which pass through it. Okay, so I've drawn 3 chords, which means we're considering 3 midpoints so far. If I zoom in, here perhaps. Okay, so maybe that's where the midpoints are, somewhere like that, I guess. And looking at that, it's a pretty rough drawing, so maybe you'd conjecture that they are centered at P, at the point P, and that's fine, but we don't want to go about trying to prove something if we aren't really very certain that it's true. So let me quickly look and see if there's a counterexample. Let's look at an edge case, and what I mean by that is a kind of extreme case where P, the point P, is right near the circumference of the circle. Okay, and so now that we have our edge case, let's see if that is going to help us at all. So I'm going to consider this chord, and I'm going to consider this chord. Okay, and let's look at the midpoints then. One of the midpoints is about where P is. And one of the midpoints is way away from P, okay? So if P were the center of the circle, we would expect all these midpoints to be equidistant from P, and that clearly is not the case, just looking at this. So we've easily found a counterexample. So that's not where the center is. However, maybe also, and I mean, you might conjecture this, or you might just move on to another strategy. It doesn't really matter. I know I conjectured this. If we consider the center of the circle, and we'll call that O, okay, perhaps, just perhaps, the center of the circle that we're considering, the second circle, is going to be halfway. It's going to be the midpoint between O and P. And maybe you'd conjecture that, but you don't have to. Okay, so we talked about how we might conjecture something about needing the center of the circle, and that's fair, but also there's other good justifications why we might start thinking about the center of the circle. Consider the fact that we're actually considering, okay, consider that we're considering midpoints. And midpoint information is not that easy, or there's not that many ways to translate it into other information. And especially when we're talking about circles, one of the main ways is going to be with maybe you'll call it the perpendicular bisector theorem, because a bisector is pretty much a midpoint. And the perpendicular bisector theorem says that if we have a line like this, and we have a line that from the midpoint of that chord, and it goes through the center of the circle, it says that this angle here is going to be 90 degrees. And both that and the converse of that are true. So that is to say that the perpendicular bisector of a chord will necessarily pass through the center of the circle as well. So we have that both ways, right? So we are definitely going to be, and that theorem, well, it requires the center of the circle to work. So I've drawn in the center of the circle now, just so that we can, just because I think that it's pretty likely that it'll come into play. Okay, so the next thing I want to quickly say is, well, do O or P lie on the circle? Because these are really our only special points we're considering right now. Do O or P lie on the circle? And that's a really good question, right? Let's let's have a look at how we might determine whether that's the case. Well, okay, so say O was going to be the midpoint of some chord which passes through P. Well, there's a unique chord which passes through O and P. There's a unique line which passes through any 2 points. And we know O is the midpoint of this because it's the diameter. It's the diameter of the circle because there's a chord that passes through the center, right? So O is the midpoint in this case. And so straight away, we know that O lies on the circle. O lies, or if we use the notation from the question, we would say O is in the set, which I don't even know what that Greek letter is, but I'll just write a lowercase w. So now, what about P? Could P also possibly be in this, right? And so let's draw a chord. Well, let's imagine we're looking for a chord of which P is the midpoint, right? And our question essentially is, does such a chord necessarily, does it necessarily exist? And maybe that will be obvious to you that it should, or maybe it won't. Okay, so I'll give one justification for why it exists. So let's suppose that we have such a chord, and we know from the perpendicular bisector theorem that since P is the midpoint, then OP is going to be at 90 degrees, right? So we can do this the other way around. We can start with OP, okay, and we know that there's going to be a perpendicular line, of course. We can always find a perpendicular line to OP, which passes through any particular point, P, right? So we can always construct such a chord of which P is the midpoint. And from the perpendicular bisector, we know that will be the midpoint because this angle is 90 degrees. Right? So now we know O and P are on the circle. And what can we conclude from that? Well, OP is going to be the diameter of this circle. Right? And as I conjectured before, we have the midpoint of OP is going to be the center of the circle. Let's call that, how about let's just call that R. We've reduced what was a seemingly difficult problem or complicated problem to a much simpler one. Now we just have to consider, whoops, that was not a line. We just have to consider one arbitrary chord which passes through P, and we have to show that the midpoint of that chord, which I'll call perhaps M for midpoint, we have to show that the midpoint lies on the circle which has diameter OP and is centered at R. Okay, so we can draw lots of lines here, like here's a radius, right? And we also have this line here, and this line OM is actually particularly important. And that's because, well, what we know is that in the big circle, M is the midpoint of a chord in the big circle. And we're going to use the perpendicular bisector theorem once again, and we can see, okay, that the angle, and I'll write this separately, the angle, which is PMO, is equal to 90 degrees. And that's true, that's necessarily true because, well, M is the midpoint of that chord, right? And it's going, and MO is of course going through the center. And so this angle here is 90 degrees. But also, if OP is going to be the diameter of some little circle, right? From the converse of Thales' theorem, we know that if OMP is 90 degrees, then OM must lie on the circle, right? That is part of Thales' theorem, that M must lie on the circle if OP is 90 degrees. And that's what we wanted. So we've shown this by using a bunch of different theorems, but basically they were just little insights that kind of stacked up.